So today what we shall discuss is something called coordinate vectors. Okay. So let's see what's a coordinate vector. Uh, Say you have a vector space, okay, so which is denoted as something like this, and each say point represents a vector in this vector space, and it has some basis. Okay, so the basis is a subset from this vector space where the span of this subset is the entire vector space. Then we call that as a basis, right? So let's call that by name up to Vn. Okay, so which means it has a n dimension vector space, so it is being represented by n vectors in the basis set. Okay, now any other vector, let's say a vector v, okay, that can be written as a linear combination of these basis vectors, right? Like c1 v1 plus c2 v2 plus dot 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 plus cn vn. Okay, right. Now there is a possibility that there are other vector sets which could be basis, right? Even in the previous uh, what to say example, for polynomial, we had a basis set like 1x x square, something like that, and also then we had the orthonormal basis set. That is also a basis set where I could represent any vector using these vectors, but that basis is different, this basis is different, right? Okay, now when I try to represent a vector through the basis vector, okay, maybe the representations will be different, maybe the linear combination will be different, but still we are talking about the same vector. Okay, so then when I represent a vector, okay, there is another way we can represent where this vector v, okay, but I could represent like b. To represent that, it's a uh, b basis, okay, this basis, okay, and that is equal to, I don't have to represent that it's a v1 c1 plus c1 v1 plus c2 v2. All I have to do is I could just tell these coefficients, right? That is sufficient. Okay, so these coefficients are called coordinates. Okay, and this way of representing is called coordinate vector. Okay, the coordinate vector which is valid only for this particular basis. If I change the basis, then the numbers are different. Okay, it is same like, say in this xy plane. Okay, so there is some vector. Okay, say there is some vector. Okay, so which I represent that vector in an xy plane. Say there is another axis or coordinate system. Okay, say this is x, this is y, but there's another coordinate, say this is x prime and this is y prime. Okay, the same vector. Okay, but in xy plane it will have some number, and in x prime y prime it will have some other number. Okay, so those numbers are nothing but the coordinates, right? Yes, sir. Yeah, so that's what. Okay, now let's see some examples. uh, let's say a polynomial 3 plus 2x plus x square, which belongs to the polynomial of order at most 2, right? Okay, now let's say the basis vector basis set is 1x x square, Okay, then I could write, let me call this as V. Okay, then V in the B is equal to 3 comma 2 comma 1. Okay, so normally this linear combination, it's not necessary that it has to be in some order, but when we write it as a coordinate, it's better. Yeah, it should be in some specific order. Okay, because 3 to 1 is different from 1 to 3. Yeah. Okay, so now, so once we represent some vectors, some unusual vectors which we have discussed, if we represent it like this, then what we could do is these coordinates itself behave like a vector space. Okay, like for example, we have three numbers, then it looks like a vector in R3 space. Okay, and then with an understanding of the R3 space, then we can do all the analysis and everything. Okay, right. And then because say if I have vector V, okay, if I represent that vector V in VB, and there is a vector W, and if I represent that vector on the same basis B, then the sum is same as if I add these vectors. Okay, add this V and W vectors, and then if I represent that in B, it is same as this one. Okay, and the other property is C into V. Okay, this is same as C into VB. So once I represent that in a coordinate as a coordinate vector and then scale it by C is same as first scale it and then represent it in a coordinate. Okay, right. So now let's see the some advantage. Let's say an example. Okay, so in this example, uh, so some vectors from R4 space. Okay, so some vector set, okay, and which is defined as 0 comma 2 comma 0 comma 1. Okay, and another vector is comma minus 1 1, right, and the third is 1 0. Okay, so these are the vectors. Now the question is, are they linearly independent? Okay, so all we have to do is we have to check whether they are linearly dependent. If they are linearly dependent, then yeah. Okay, so what is the condition for linearly dependent? The condition is c1 into the first vector plus c2 into the second vector plus c3 into the third vector. That should be equal to 0 0 0 0, the zero vector of R4 space. Okay, and from this you could get some equation for as a linear system in terms of c1 c2 and c3, and if you solve and if you get a only solution which is 0 0 0, then it's a linearly independent. Okay, if you get anything else, then it's a linearly dependent. Okay, so I leave that as an exercise, but if you solve it, you will get everything as 0. Okay, fine. Now another example. Okay, the same question, they have given three vectors but in a different vector space, and they are asking whether they are linearly independent. Okay, now if you see that set C is equal to, it is from P3 space, 2x plus x cube. Okay, and the minus x plus x square plus 2x cube and
3
then 3
3 minus 2x
minus 2x
plus x square.
plus x square. Okay, and then once again what you need to do is c1 into first plus c2 into second plus c3 into third should be equal to 0 0,
0 0.
the 0
0
vector
into
on
x
the p3 space.
plus
Okay, then you have to
get
check
c1 c3 exists.
the system of equations by
As
equating
unique
each the
like
coefficient of the particular
terms.
order of x, a particular degree of x,
Yes,
right? So like that you will generate the equation.
yes, sir.
Okay, but if you notice, if you represent these vectors, okay, as a coordinate vectors, okay, so what is the coordinate vector of the first one?
2
The basis is
0 that
0
is
x square and x
x
cube,
cube.
right? So then in that case, so
0
0
comma 2
2
0
0
1
1, right? And what about this?
0
0
minus 1
minus 1
1
1
2
2, right? And this one
3
3
minus 2
minus 2
1
1
0.
0. And if you notice, this is as same as this one, right?
Yes,
So
sir.
the coordinate basis.
Yes, sir.
So in this R4 space, if these vectors are linearly independent, then I don't have to check even here, because the coordinate vectors are same. Okay, even here it will be linearly independent. And the third example, they have put like a matrix, okay,
And
in a 2 by 2 matrix. The first one is 0 2
2 0 1
0 1, okay, and
0
then
minus 1
0 minus
minus
1
1
1
1 2
2,
3
and then
minus 2
3 minus 2
1 0.
1 0. Okay, so tell me, what is the basis set we can choose so that I will get a coordinate vector as same as this one? Or can you come up with some basis vectors for M2, so that I could represent uh, any other vectors or any other element in M2 through a linear combination of those bases?
C1 into
Hmm. So, what is the
0 2 0 0
0 2 0?
1.
No, I mean that's a vector, but the basis is what I'm asking. See, in this case, what is the basis? The basis is
0
0. Oh, sorry, 1000 is one of the bases. 0100
0
is another basis, right? And here, if you see, 1 is one basis, x is another basis vector, and x square, and so x cube. Similarly, here, what I can say.
0 0 2 1.
No. See, because with 0021, and then because what is basis?
It
I
should
could represent
any
any
vector
any vector in M2, for in this case M2, through that one,
basis.
right? Yeah.
Yes.
So tell me, how about 1000 is V1, okay, and V2 is 0100, and then V3 is 0010, and say V4 is 0001. So now, through linear combination, I could get any matrix in this space M2, right? Isn't it? Can I? Right. So in that case, tell me, say this vector, the first vector. Okay. How do I get the first vector?
0 into V1
0 into V1
plus
plus
2V2
2V2
plus
plus
0 into V3
0 v3
plus
plus
v4.
1 into v4.
Yes.
Okay,
Yes.
so now in the coordinate, as a coordinate vector, how can I write?
0 2
0 2
0
0
1.
1. Okay, similarly, how do I write the second vector?
0
0
minus 1
minus 1
1
1
2.
2. Okay, and third one?
3
3
minus 2
minus 2
1
1
0.
0. Okay, now once again, are they linearly independent? The question is, all you have to do is, because those coordinate vectors are same as this one, so they are also linearly independent. Okay,
Yes.
so that's the advantage of working with the
Base.
coordinate vectors. Okay, right. So now this is an exercise. Okay, so you have a vector 2 plus 7x plus x square, which is a vector belong to P2 space. Okay, now the basis vector is,
X plus x square.
yes, x
1
plus x
plus x
square,
square.
1 plus x square, and
1
then
plus x.
1 plus x. Okay, now let's say this vector, let me call that vector as v. Okay,
B.
then what is vb? Or how do I put, yeah, what is
C1
v in the b basis? Okay, so this is what I want you to solve.